Hey everyone, welcome. This is Ayhan. Today I'm gonna walk you through the solution to first problem of 2024 International Mathematical Olympiad. Now before we touch a single formula, let me tell you what my videos are really about. They are not just about solving problems, they are about building analytical thinking. Here's the thing, and I tell this to my friends all the time. Understanding the problem is already 15% of the solution. The other 50% is reaching the answer by thinking simply. Simple thinking, not fancy tricks, not genius moves. My real goal here is to help you develop that mindset. I want to show you how to slow down, understand what the question is truly asking, and then let the solution almost reveal itself. Let me be honest with you for a second. I'm almost 50 years old, and after decades of solving problems and writing algorithms, I've learned something very clear. When you are solving a problem or even writing code, the only things you actually need are focus and simple thinking. And from my experience, I can tell you this with confidence. In IMO style competitions, even a student with average intelligence and average math skills can succeed. You don't need to be a prodigy. You don't need to be the smartest person in the classroom. You just need one golden rule. Know your basic math and think simple. All right. All right. Let's read our first problem together. Let's read. Determine all real numbers alpha such that for every positive integer n, the integer floor of alpha plus floor of 2 times alpha plus floor of n alpha is a multiple of n. Note that z denotes the greatest integer less than or equal to z. For example, floor of minus pi is equal to minus 4 and floor of 2 equals to floor of 2.9 equal to 2. Now, before we do any real solving, I want to do something that smart problem solvers always do. We are going to zoom out and ask, what do I actually need to know to even understand this question? And honestly, there are only two key ideas hiding in here. First, what is a real number? Second, what does positive integer mean? That's it. Those are the two big vocabulary words that matter. Now you might also notice those bracket looking stretch symbol in the problem. So that's the floor function, and I will absolutely talk about it in this video. But let me be super clear. You do not need to know the floor function ahead of time to solve this problem. Seriously, the problem literally tells you what it does. It could have used a unicorn symbol or a spaceship symbol, gave you a rule, and with still solve it the same way. So don't get distracted by fancy notation. Good problem solving is about focusing on what matters and ignoring what doesn't. Now, let's talk about the first key idea, real numbers. What are real numbers? Look at this picture. The big yellow box is the set of real numbers. So basically, any number you can place on the number line leaves somewhere inside this big box. Now inside real numbers, we have two main families, rational numbers and irrational numbers. Those are the numbers I am talking about rational numbers. Those rational numbers are the numbers that can be written as a fraction, a over b, where a and b are integers, and naturally b must be different from 0. But here's the more student-friendly way to recognize them. A number is rational if its decimal form either ends with any numbers like 0.5 or 2.145, or repeats a pattern forever like 0.17777. Rational numbers are divided into a number or family subgroups. One of them is integers. You already know these. Non-fractional numbers from negative infinity to positive infinity. Or you can say the fraction is 0. For example, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4. Another of these subgroup is whole numbers. These are integers that go from 0 to infinity. For example, 0, 1, 2, 3, 4. And natural numbers, typically 1, 2, 3. Sometimes people include 0, but we'll be careful about definitions. So rational numbers are basically like most of the numbers you've been using your whole life. And second numbers, irrational numbers, these are the weird but famous ones. They cannot be written as a simple fraction and their decimals go on forever without repeating. Examples on the slide: pi, square root of 3 minus e. So their decimals fly off to infinity, but not in a repeating pattern. So when you combine all rational numbers plus all irrational numbers, you get all real numbers. That's what real number means in this problem. Why are we doing this? Because the problem says find all real numbers alpha such that, etc. So alpha could be a fraction. Alpha could be an integer or a decimal or pi or, for example, square root 2. Literally anything on the number line. Now, the second keyword is positive integer, and that one is much easier. Positive integer are just 1, 2, 3, 4, and so on so forth, greater than 0. And when those two definitions are clear, the problem suddenly feels way less scary. That's the lesson I want you to notice. When you strip away the noise and focus on definitions, what looked complicated turns into something clean and manageable. All right. Now that we speak the language of the problem, we are ready to actually attack it. So here's the thing, the problem already tells us exactly what the rule is. We are not expected to know anything extra. That symbol that looks like square brackets is called the floor function. But honestly, at this point, the name doesn't really matter. We didn't know its name before. Now we do, and that's nice. But for solving this problem is basically irrelevant knowledge. Now, according to the rule in the question, namely the floor function, the floor of a number is greatest integer less than or equal to the that number. In plain English, you round down, always. In the example on the screen, we are taking the floor function of x. This x can be 2.9 or 5 or -4. We are interested in the floor of x. Floor of 2.9 is equal to 2, value of 2. Floor of -3.2 is equal to -4. Floor of 5 is equal to 5. In summary, we can say that the floor function of x is the largest number less than or equal to x. Now, let's translate the question into everyday language. We are given a real number alpha. For every positive integer n, we look at this sum, floor alpha plus floor 2 alpha plus 3 dots plus floor n alpha. The problem says this sum must be a multiple of n for every positive integer n. In other words, if we divide the sum by n, the remainder must be 0 for all values of n. Here the value of n can be 1, 2, 3, 4, 5, so on and so forth. That's a very strong condition. I will give you a small example to understand the goal. Suppose n is equal to 3. Then sum is floor of alpha plus floor of 2 alpha plus floor of 3 alpha. The problem wants this number to be divisible by 3 because there are 3 numbers in total, and the same thing must work for if n is equal to 1, if n is equal to 2, or 100 or 1 million. So for every single one. Okay, so the big question is which real numbers alpha are so special that this always happens. Alright, now that we fully understand the mission, let's start solving. Let's slow things down and really enjoy this step because this is one of those moments where math is actually being nice to us. We're gonna start by testing the simplest possible candidates, even integers. So let's make a clean assumption. We say alpha equals 2m, where m is an integer. In plain English, we're assuming alpha is even. That's it. Now look at what happens next. For any number k, when we multiply alpha by k, we get k alpha equals 2mk. And since 2mk is already an integer, taking the floor does absolutely nothing. So floor of k alpha equals 2mk. This is beautiful. No rounding issues, no surprises. Now, let's build the sum the problem is asking about. For k is equal to 1, 2, 3 to n, we get 2m plus 4m plus 6m plus 3 dots plus 2mn. Take a second and just look at the pattern. Every term has a 2m in it. So of course we factor that out. 2m times open parenthesis 1 plus 2 plus 3 dots plus n close parenthesis. And here is a formula every math student should know by heart. 1 plus 2 plus 3 dots plus n equals n times open parenthesis n plus 1 close parenthesis all over 2. Once we plug that in, everything falls into place. 2m multiplied by n times open parenthesis n plus 1 close parenthesis all over 2 is equal to n times open parenthesis n plus 1 close parenthesis. Now pause right here. This is the key moment. That final expression clearly contains a factor of n, which means the entire sum is always divisible by n. No conditions, no exceptions, no tricks, and that's why we can confidently say every even integer works. Okay, now we can say that every integer works. All right, we are now in step 2. Let alpha be an arbitrary real numbers. Every real number can be written in the following standard form. Alpha equals k plus epsilon, where k is an integer and 0 less than or equal to epsilon less than 1. In other words, any real number consists of an integer part k and a fractional part epsilon. Now let's pause for a second and recall what the problem is asking. The question involves the sum floor of 1 times alpha plus floor of 2 times alpha plus floor of 3 times alpha all the way up to floor of n times alpha. So we rewrite this entire expression in a compact form as S sub n equals the sum from j equals 1 to n of floor of j alpha. Here's what this means in plain English. J is just a counter. It processes values from each value of j, selects one term in the sum. So when we zoom in on a single term, we are looking at floor of j alpha. And this is exactly why we multiply alpha by j, not because alpha is real, but because the problem itself already does that. Since we are dealing with j alpha, we substitute alpha equals k plus epsilon. So naturally, j alpha equals j times open parenthesis k plus epsilon close parenthesis equals jk plus j epsilon. This follows directly from the structure of the problem. Now we apply the floor function to j alpha. Okay, now we apply the floor function. Floor of j alpha equals floor of jk plus j epsilon. Since jk is an integer, the floor function separates nicely jk plus floor of j epsilon. This works because n naturally splits into a whole number part and a fractional part. Now that we've written the expanded form of j alpha, we can express it using the summation formula we know. In the summation formula, the value of j will be from 2 1. As you can see, we express this sum as S sub n. In the formula above, That was the result when we took the floor function of J alpha. Floor of J alpha was equal to Jk plus floor of J epsilon. Now, when we expand this into the explicit form of the summation formula, S sub n is equal to sum of the numbers from 1 to n with a common factor of k, and the sum of the floor functions of the epsilon values from to n. And remember, epsilon between 0 and 1, but epsilon is not equal to 1. So, floor of epsilon is 0. So, we can now write S sub n is equal to k multiplied by n times open parenthesis n plus 1 close parenthesis all over 2 plus t sub n, where Tn consists of floor of epsilons. Here T sub n floor of epsilon plus floor of 2 epsilon plus floor of n epsilon. Now look carefully at this expression. We see the variable k sitting right there. And since k is an integer, it must be either even or odd. And that's exactly what we are going to text next. Okay, in the upper right corner, you can see the formulas for the total sum and alpha again, enclosed in a red frame. Please remember them. Now, here's the k observation for case A. If k is even, then the first term k multiplied by n times n plus 1 over 2 is always divisible by n. That means this part causes no trouble at all. So the entire problem now comes down to understanding the second term. T sub n is equal to summation of floor of epsilons. This is where all the action is. Now notice the following. We always have 0 less than or equal to epsilon less than 1. Since n greater than 0, we can multiply every part of this inequality by n. So what happened? 0 less than or equal to an epsilon less than n. Now we will take the floor of the entire expression that gives us floor and epsilon belongs to the set 0, 1, 2, 3 dots and minus 1. So automatically we conclude 0 less than or equal to floor and epsilon less than or equal to n minus 1. Now here's the crucial point. Among all the numbers in that range, the only multiple of n is 0. And that fact is what drives the rest of the argument. Now, let's make this concrete by looking at a couple of examples by checking whether they really satisfy this n-1 rule. Example 1. Let epsilon be 0.3 and the value of n be 5. Then n epsilon is equal to 5 times 0.3. So it is equal to 1.5. So floor of 1.5 equals to 1. Indeed, the value of 1 lies between 0 and 4. Next example, example 2, let epsilon be 0 and the value of n be 7. then an epsilon is equal to 7 times 0, so it equals to 0. And floor of 0 is equal to 0. Indeed, the value of 0 lies between 0 and 6. Therefore, in the case where k is even, the first term is already divisible by n. There is no problem here, and the second term is stuck between 0 and n minus 1. Thus, the only possible multiple of n in this interval is 0. Alright, let's go back to the idea of being even. We already showed floor of an epsilon between 0 and n minus 1. Now here's the k observation. The only multiple of n in that range is 0. So we are forced to conclude floor of an epsilon is 0 for all n. Why is 0 the only possibility? Let's think about what multiples of n actually look like. They are 0, n, 2n, 3n, 4n, so on and so forth. Now compare that list with range 0, 1, 2, 3, 4 to n minus 1. Here's the important observation: n is not in the list, and n is way bigger. Negative multiples weren't allowed, right? So guess what happened? The only multiple of n in that entire range is 0. That's exactly why we say the only multiple of n in that range is 0. What does this force epsilon to be? Now remember, epsilon between 0 and 1, but epsilon is not equal to 1. Since n greater than 0, multiplying by n gives an epsilon between 0 and n. And we know that floor of an epsilon is equal to 0. This means an epsilon between 0 and 1, but not equal to 1. If we divide this formula by n, we get epsilon less than 1 over n for all n. Now think about this carefully. There is only one number that is smaller than 1 over n for every positive integer n. And that number is epsilon is 0. Final conclusion of the even case: since epsilon is 0 and alpha is equal to k plus epsilon, we get alpha is equal to k. And because we are in the even case, k must be even. So final conclusion is crystal clear. Every even integer works in this case. Now let's focus on the case where k is odd. The sum has the form s sub n is equal to k multiplied by n times open parenthesis n plus 1 close parenthesis all over 2 plus t sub n. And the condition of the problem says s sub n is congruent to 0 mod n. In other words, the total must be a multiple of n. Here's the issue. When k is odd, the term k times n times open parenthesis n plus 1 close parenthesis all over 2 is not always divisible by n. So the responsibility of making the whole sum divisible by n falls entirely on the second term Tn. That means Tn has to compensate for whatever remainder the first term leaves module n. Recall that 0 less than or equal to epsilon less than 1. Multiplying by n, we get 0 less than or equal to n epsilon less than n. Taking the floor, 0 less than or equal to floor and epsilon less than or equal to n minus 1. So, floor of n epsilon can only be one of the numbers which can be 0 to n minus 1. For example, 1, 2, 3, 4, 5, n minus 1. Now, here's the key point. To fix the remainder caused by the odd k, floor of n epsilon must produce a remainder of minus 1 module n. The only number in that range is n minus 1 because n minus 1 congruent to minus 1 mod n. So we are forced to conclude floor of n epsilon is equal to n minus 1. What does floor of n epsilon is equal to n minus 1 actually mean? A floor equation translates directly into an inequality. In general, floor of x is equal to m if and only if m less than or equal to x less than m plus 1. Here, x is n epsilon, m is equal to n minus 1. So we get n minus 1 less than or equal to n epsilon less than n. Now divide every part of the inequality by n. Remember, n is positive. N minus 1 over n is less than or equal to epsilon less than 1, which is exactly 1 minus 1 over n is less than or equal to epsilon less than 1. As n gets bigger, that left side gets closer and closer to 1. That would force epsilon greater than or equal to 1. But we already said the epsilon value can be equal to 0, but it cannot be equal to 1. In fact, it must be less than 1. That's contradiction. So, odd integers are impossible. So, no solution exists when k is odd, you see. After all this research, we can say this. The only real numbers alpha that satisfy the condition for every positive integer n are all even integers. In this problem, we analyze a sum involving the floor of multiples of a real number and ask when that sum is divisible by every positive integer n. By separating the real number into its integer and fractional parts, we discover that the condition can only be satisfied when the fractional part disappears completely. As a result, the only real numbers that work are even integers and no other values can satisfy the requirement. Okay, we've solved this Olympic question. Thank you for thinking along with me. See you in the next problem solving session. Bye.